Alright, time for another draftphysics.com, debatephysics.com also, but yeah, pointless. Yeah, so can't really debate, just, nonsense. So they're basically arguing that yes, 2 pounds doesn't weigh 2 pounds. Um, no, but it weighs 4 pounds or something. I don't know. It weighs 1.4 pounds. It's just too ridiculous. Scales don't work. Hook was a retard. Anyway, just, you know. So, just looking at the icon for this video, you're saying, why is he putting the weight on top of the rubber bands? I mean, obviously, you would hang the weight from like a hook that would be the same for any weight you put on. You have the same hook. You don't let the shape of the object fuck up the rubber band. I mean, it's just, we've been over these things so many times, and they always just find a way to do it in some ridiculously stupid way. And you're just like, oh, I can't. So we know this is just going to be a garbage video. So let's play the garbage.
Just a trio of...
Oh, jeez. So, nowhere near the dimensions of the dispar rubber band. So, we'll see if he stretches it further. But yeah, not even close. Let's see if I can center this better. All right, continuing.
little things I thought was interesting to see. The deformation of an elastic band here, what difference it would make if it was stretched. So we got two nails, two different positions.
Good.
It's only a visual check, as a rough idea. Intuitively you would say that it must make a difference because one would be a lot tighter than the other, but I thought, well, I better just prove it anyway. So we got this slack in this position.
So really, there's, like I said, the shape of the object is really going to change how much the rubber band stretches. Because a whole bunch of here, 50% of the rubber band is going to be in contact with the object. In the other case, it's going to be, 10%. But anyway.
It's about a 3/4 pound.
Yeah, brilliant.
About a 3/4 pound weight.
So again, you're saying, why wouldn't he just put a string through the hole in the weight, make a little metal hook, dotted wire, hook it on the rubber band? Why is he putting the object on top of the rubber band? I mean, just like, it's not even a way I would even imagine doing the experiment. It wouldn't even occur to me to actually put a duck on top of the rubber band. I would always think to measure the weight below the rubber band in gravity.
And it's just below this top line there.
Yeah, very precise measurement. Thank you.
This line just below. With the same weight. It is stretched across there.
I don't know. There's some nails in the way here, but whatever, doesn't matter. Well, it doesn't go below, so.
It's definitely not as far. Which is intuitively the case, isn't it?
And the real question is when does it obey Hooke's law? So you really should just have two masses, one mass and a two mass, and then you can see if Hooke's law is obeyed. You can see if twice the weight is twice the weight. If it's a scale, if it actually measures like a scale, or does it do something not like a scale? The whole point is to see if it obeys Hooke's law, because all these experiments mean nothing with rubber bands if they don't obey Hooke's law. You can't use the measurements to mean anything.
Back on there. Much deeper sag. So that sort of is right. We can't.
So it really, again, but if you want to do it right, you should be hanging it so you're putting the same pressure, the same amount of spring of rubber band is doing the stretching. It's not sticking to the material. So, and again, you'd probably have even more dramatic outcome in terms of the compression if you actually did the experiment right. It'd be even more obvious.
Measure whether this is conforming to Hooke's law, because we're not measuring the stretch of the spring, we're measuring the downward deformation. It's a bit more tricky, but it was just to show whether it would actually...
The downward deformation would be the same for Hooke's law. I mean, the fact that there's two sides doesn't make much difference. It still should obey Hooke's law, I believe. Let me just, you do have to think about this stuff. I mean, the stretch should still be, the fact that it's diagonally stretching instead of up and down stretching. Just not sure, but I'm pretty sure it doesn't matter. But yes, ideally you would just use a rubber band straight this way, ideally.
Sag further. But of course, as long as both, if this elastic band was catching something as a measurement of energy, as long as you use the same configuration, if you were launching...
So this is the same guy who found out that the spring can be overcompressed and that you have to compensate for the overcompressed spring, and he's going to say something that he knows, if he thinks about it the least little bit, oh yeah, that really can't be true, because I'm not going to get the same answer if I take a spring that's not overcompressed and I put an extra weight on that spring. That is, I already compress it a pound. Then I'm not going to have the same proportionalities. I'm only going to be adding a pound to the first weight, which would double its weight, and then the second weight, that's 2 pounds, I'm only going to be adding 1/3 a pound to its weight. So now I'm not going to get the same numbers. I mean, he should be able to figure out that, no, it does matter, moron. It matters how tight the spring is.
One mass at it, and a different mass and a different velocity, doesn't matter as long as you're using the same configuration. But Hooke's law is irrelevant to it, because...
It's not irrelevant. It's the only way this experiment can mean anything. If Hooke's law doesn't apply and 2 pounds doesn't create twice the compression, then how are you measuring anything? It's not a rational measurement of anything.
We're measuring the energy stored in the thing, which has nothing to do with Hooke's law. Hooke's law is just about...
It's idiotic, of course. The Hooke's law doesn't have anything other to do with anything other than pointing out that there's in a proportional way that this rubber band or the spring stores energy. It stores it proportionally. 1 mass, 2 mass, twice as much. 3 mass, 3 times as much. 4 mass, 4 times as much. It's critically important. Scales aren't of any value as a measurement tool without it. Without Hooke's law, this isn't a measurement tool anymore.
The linear deformation with a force on an elastic body, that's not a measurement of energy, as we know.
I don't know. I don't know who says that. Okay, I don't even know what physicist. Can you show me a physicist you're quoting who's ever said this in a lecture, that you're not storing energy in springs? I mean, it's ridiculous.
And this is in response to you, Gary, when you say this video I made about lifting your method, comparing the two methods.
There's no method. I didn't have any fucking method, you cunt. So this is just such nonsense. This moronic notion of yours that this is about how high you lifted a weight. It's just about how much pressure you're putting on the spring, and whether 2 pounds is twice the pressure on the spring. You're claiming it's magical, somehow 4 pounds, somehow it has extra pressure, that somehow it's storing extra energy, that somehow the second mass is doing something the first mass isn't doing. Or that collectively 2 masses magically reproduce and create children, and the children have extra energy or something. It's an idiotic, nonsensical pile of crap that you're arguing. Hooke's law basically said, and your own experiment proved, he did the fucking experiment. This fucking idiot is just sitting there, arguing against his own experiment. I mean, what's the point of that? It's so fucking retarded. So he does the fucking experiment, as he compensates for the spring that was a little bit distorted because of the issue of let's see if we can get the light better. The spring being over compressed. And so the basic idea of what he proved is that no, it's true that I put a one mass on, I get this much expansion of the spring. So it's we're just talking about the expansion part. We're just showing that. And I put a second, so that's one mass. And then 2 mass extends the spring twice as much. There. That's it. He proved it. So he puts a second mass on, and this happens. This distance. This distance is 1 mass. This distance is with 2 masses. Proving that the second mass does exactly the same amount of change in the spring. It doesn't get harder to compress. It's just as easy to compress. 2 units of force, 2 units of distance, and the distances are equal. That's Hooke's law. He proved it, and then he's arguing against it. Fucking idiot.
Of compressing a spring. Compressing a spring to make...
So they just refuse to get to understand the difference between something applying a constant force, that is where I put a weight on a scale, and it's constantly putting a force on the scale. And then when I add another weight, this weight doesn't have to do this weight's work. This weight's already doing this weight's work. It's already done the 1 pound thing. This one just has to go from 1 to 2. So it's just as easy to go from 0 to 1 as it is to go from 1 to 2. That's Hooke's law. Shit. Fucking idiot. Damn.
Measure its energy. 2 ways we can do it. We can mechanically depress the spring with a machine or with our arm, or we can lift a weight up and let the weight compress the spring. And you were saying that it didn't matter where you would lift.
It doesn't matter. You're only going to get this distance out of the spring. That's all it's going to move is this distance. The distance really doesn't say anything. I use a tighter spring, the distance is going to be smaller. Do you think it really matters how much distance there is? Different springs will allow there to be a different amount of distance. So this clearly isn't about distance. This distance wouldn't have any consistency. On one scale, 1 pound will do this. On another scale, 1 pound will do that. You think that the pounds have a different amount of energy because it's in a different spring, a different ratio of movement? No, the movement doesn't matter. So this distance shit is nonsense. It doesn't have anything to do with the subject, fuckhead.
The weight from. No, of course it does matter completely, because the weight had to be lifted from the ground. 2 distances. And I was making that distinction because you were saying
irrelevant. I mean, again, I'll just say it again. It's irrelevant. Okay, its weight is about how much the gravitational differential, and that's what the spring is going to recognize, is the gravitational differential. The fact that gravity acts first and the ground pushes up after. So the gravity is the initial action. The scale recognizes the initial action that's never compensated for, and that's what you're seeing is that differential. And all it can do is put it back to where it started from if I removed gravity. So if you put something on a scale and gravity holds it down to, say, that number, now I instantaneously eliminate the force of gravity. All that's going to do is return to 0. It's not going anywhere else. It's just going to go back up to 0.
Matter where we lift it from. It absolutely does. Before we can let the weight do its work on the spring.
I mean, the catch is that obviously when it goes back to 0, it's going to do it at a velocity. So the object, because there's no gravity, is going to keep going. So I should have pointed that out. Without gravity, yes, it becomes a constant. It becomes a constant velocity because there's nothing to take the velocity away.
We've got to lift it up. So one,
But the velocity is going to be 0.44 meters per second. All you can get out of this is 0.44 meters per second. So I put an elephant on it, okay, and I turn it, I eliminate gravity. The elephant leaves at 0.44 meters per second. Okay, that's it. That's all you get. That's what 1 unit of anything's weight is the momentum of 0.44. That's your velocity, meters per second.
pound weight, so it's a constant 1 pound force for the two distances we lift it up. And the two distances are
As I pointed out already, it depends on what speed you lift it up. If you lift it really slowly, you'll put in thousands of joules of energy. If you lift it up quickly, at the speed of its falling speed, the speed it would have when it hit the ground, if you were to drop it from that distance, that's the ideal speed, the most efficient speed to get to this height. So you'll do a lot less work.
constant 1 pound force is a measurement of energy. So if you say it doesn't matter where we lift it from, yes, that would definitely affect the energy we're putting in.
So again, if you're going to make that argument, I just make the counter argument that the second mass, I didn't have to lift it as high. So what's the point of this nonsense? But it's not 3 units of distance. I mean, it's just nonsense.
If we mechanically compress the spring with a machine or
Oh, what the fuck? Oh, okay. My fault.
using the same configuration,
My fault.
hooks and let the weight.
So again, he's trying to say that these are 3 units of distance, and that it only falls 2 units, but it's not, because if you let the spring push the weights back up, it's only going to push one of them up this far, and the other one is going to push from this distance to this distance. But whatever. Continuing.
Press the spring. And you were saying that it didn't matter where you would lift the weight from. And no, of course it does matter completely.
It doesn't matter in the sense that it's not free energy. You're obviously doing, the argument you're making is that you have to put in 3 units of work to put it on the scale. So what? There's no law against that. so again, it's not, you're not proving anything.
Because
Wasting energy is not against the laws of physics. Obviously, you'll lift it faster than it will come down on the scale. So right there, you could make the argument the scale's only going to give it it's only going to give it 4.44 meters per second of velocity when it lifts it back up. It's going to lift it up very slowly, where you lifted it presumably at the ideal speed, which would be its falling speed, its falling velocity, its maximum velocity when falling. If you lift it at that speed, or you launch it at that speed, right? If you're constantly lifting, I don't know what the numbers would be. But the idea is the less time you're in the gravity, it's the same time as the falling time. So if you lift it at the same, using in the same amount of time to get to from point A to point B, you'll do the same work. Time is all that matters. So the very slow expansion speed of the spring isn't going to be anywhere near as efficient as the speed you lifted the weight at.
it has to be lifted from the ground. 2 distances. And I was making that distinction.
And I'll say it again. I'll just say it again. Well, you already have heard me say 4,000 times that it's about time. And then I don't even think how you could even argue that it isn't more work if I lift something slowly. If I lift it slowly, I have to do a lot more work than if I just lifted it quickly.
Where we lift it from. It absolutely does. Before we can let the weight do its work on the spring, we've got to lift it up. It's a 1 pound weight, so it's a constant 1 pound force for the 2 distant.
How did you? Where did you do that? Where did you do this constant 1 pound force? None of that happens. That's not how the spring is going to lift it back up. So that's not true. You're not lifting it at the same speed the spring is going to lift it back up. So it's just bullshit.
This is we lift it up. And the two distances at a constant 1 pound force is a measurement of energy.
So again, he just keeps ignoring, like so many times I've done this, okay, and he just keeps ignoring it. You put something on the scale, you mark that amount of compression, right, and you just turn the scale sideways. What's that speed? yeah, what's that speed? The argument that speed is always, no matter what object you put on this here, and you're going to push it here, that speed will always be 0.44 meters per second.
So if you say it doesn't matter where we lift it from, yes, that would definitely affect the energy we're putting in. If we mechanically compress the spring with a machine or our arm, then we're applying the force from the top down. But we start off with zero force and it gradually increases.
So again, you says you. So you can keep saying things like that, and that's your prerogative. But there's no reason why when something's being pushed by gravity, that's a truth for the thing being pushed by gravity, in the sense that, yes, the scale just tells you where equilibrium is. It just tells you where now the force you're applying down equals the force up. So when you first hit the scale, you still weigh 150 pounds. And the scale's not providing any resistance. And it's not until you reach a point on the scale where the force in the opposite direction is 150 pounds do you stop moving, or does the spring stop compressing. So, the constant force is 9.8 meters per second. That's the constant force that you have to overcome. But the fact is, it will give you a certain velocity on your way. And you can't deny all these truths. But there's no way you're going to be able to do the math for how the velocity, the acceleration will be constantly changing as the mass falls. And it will eventually slow down and stop. It starts off moving very fast. It ends up moving very slow. But we can't see any of it, frankly.
So the average will be 0.5 and 1.5. The first weight is a constant 1 pound force, two distances. So that's more than this first compression by manually compressing the spring. You're completely off kilter again.
Oh, fuck you. You're the one off kilter. You think these two objects magically, right? I put this on the scale, it's 1 unit of energy. I put this one on the scale, it's 1 unit of energy. Somehow, when I put them both on the scale, it's 4 units of energy. You can't get more off kilter than that, fucktard.
And lastly, but not leastly, you keep going on about my video I haven't taken down. It's
the absolute lie video.
Correct.
Okay, so I mean, it's just insanely stupid. If you shoot the damn thing in a straight line across, okay, off a cliff, you launch it. The fact is, they're both going to fall at exactly the same time. They're both going to hit the ground at the same time. If one's going twice as fast and in the same exact amount of time, then it'll go twice the distance. It will not go 4 times the distance. It's just an absolute lie. I can't believe you're going to defend it. You're a fucking lying sack of shit.
Two different velocities the same way. One velocity launching the ball off of a ramp with a little upturn in it.
Alright, so now he changed the video. There wasn't a little upturn in your fucking video, you jackass. So now he's doing this fucking bullshit where he's going to sit there and shoot the object up into gravity to change the amount of distance, because now he's changing how far they get to fall. So obviously if you shoot the object up, you're going to change the amount of time it has to fall. The whole point of shooting them straight, man, they fall the same distance. If you're going to change how much distance they're going to fall, then you change the experiment. So all I can do to counter your argument is get rid of the ground and put the ground 500 miles lower. Then all of a sudden we're right back where we start again, and it's going to be 50, 1/2 the distance. All you're doing is changing how much time they have to fall. The more equal the time is they're going to fall, the more likely it is it's going to be twice the distance, okay? You can't avoid that. So all I have to do is give them more falling time, then your little fucking bullshit, the little tiny bit he'll arc up, will be a tiny percentage of the falling distance. So the smaller that arc up is as a percentage of the total distance, the more and more and more it gets consistent with being, 50 to 100 feet or whatever, 2 to 1. So fuck you, you lying sack of shit. I mean, just can't believe he's going to lie about what his video said. That's not what your video said. Your video didn't say anything about a little arc up.
We'll go one distance. Doubling the velocity, it goes 4 distances.
Alright, so just a lie. It doesn't happen. Alright, and if you give them more falling distance, again, if you make the falling distance equal, alright, it has to be 2 to 1. Liar. God, I can't believe how pathetic these fucking people are. The video is a complete deception. He obviously didn't know what the fuck he was talking about. And instead of admitting that he made a huge giant mistake, now he's going to redo the video and pretend, oh yeah, I was talking about the video not in a straight line. Even though I drew a dead straight line, no, I was really meaning you arc the objects up in the air. See, and the higher velocity will go higher in the air, so it'll have more falling time. What a piece of goddamn human garbage.
Just for the addition of that theorem. Absolutely correct. I'm not going to take anything down. Deal with this question, boy. Why does the two velocity mass go 4 times the distance?
It doesn't go 4 times the distance as long as you, if you change if you make it again even, the amount of time they're allowed to be free falling. So if you restore their free fall time to being more like the same, that is, you lower you just make more distance for them to fall, it'll get closer and closer and closer to 2 to 1. You fucking idiot.
Distance.
God, what a liar. Oh, God, disgusting. Disgusting liar.
In this video, I'm going to show...
I mean, he clearly didn't say that in his video, right? I mean, it's just clear he did not say in his, oh, what if I shoot him up in the air? You could see the straight line. Oh, God. He even admitted it in the comments that he was wrong. Here he is sitting there defending it. God, what a piece of garbage. All right, well, enough of that. I just shouldn't bother with these morons. This is just too ridiculous. 2 pounds weighs 4 pounds. I mean, let's say you're dropping something. Okay, so I'm arguing that on a scale, right? These two objects are the same energy, right? I put this on the object, same energy as this, same energy. Now, if I drop them onto the scale, you could understand that, yes, if I drop them the exact same distance, they'll have to create the same deflection. You know, same distance, same deflection. All right? And so, it's just, you have to logically just say, okay, there's no fucking way, all right, that even if I'm going to drop the weights, all right, that 2 weights can be less than twice the deflection in the scale. I can't hit the scale with 2 weights and get a reading that's only 1.5 weights. It's not possible. I mean, a 2 mass can't weigh 1.4. No, it has to weigh 2. So it's just they're just too fucking stupid. Planet of the too fucking stupid. That's what we live on. Ugh.